So this video will be about some applications of the ideal gas law and Dalton's law of partial pressure. Now, the first of these, I'm not sure if you guys would have done in your first year chemistry course. That's the applications of the ideal gas law. Dalton's law of partial pressure, I'm sure you've heard of before, and we'll look at kind of the more conceptual part of that and using that in order to solve problems and how you go about doing that, and specifically the relationship between partial pressure and the number of moles of gas. So let's start off with this application of the ideal gas law. We have an ideal gas, and we have 0.5 grams of an unknown gaseous compound. We know its volume is 13 liters. We know its pressure is 0.7 atmospheres, and the temperature is at 25 degrees Celsius. And the question is, what is the molar mass of the gas? This is a very, very popular question for the AP chemistry people. They love to have you guys calculate molar masses using experimental data. And one of the ways that you can do that is by having a certain mass of a gas and finding out what the pressure and volume is at a certain temperature. And to do this, all you have to do is you use this ideal gas law. So we're going to have PV equals nRT is our equation. And what we want to know is we want to know how many moles of gas we have, because the molar mass, crazy thing, the molar mass, we define that as equal to the grams per mole. Now we know how many grams of gas we have. It's 0.5. So if we know how many moles of gas we have, we can just divide those two and figure it out. And to find the number of moles, we're going to use the ideal gas law since we know, the other three variables. So in this case, I'm going to solve for n using algebra, the famous algebra arrow. So n will be equal to PV over RT. And we can just plug numbers in. So we'll have 0.7 atmospheres, volume of 13 liters. Then we have 0.08206 atmosphere liters per mole Kelvin. So again, always watch units here. And our temperature, remember, has been Kelvin, so that's going to be 298 Kelvin. So 25 degrees Celsius is 298 Kelvin. And we do all that, and what we're going to get is we have 0.212, maybe carry an extra sig fig, moles. Okay? So we have the number of moles now. And now to get the molar mass, all we have to do is take the grams that we had, 0.500 grams, divide it by 0.2126 moles, and we will get 2.35 grams per mole for this gaseous compound. So maybe it's some freaky form of helium or some bizarre isotope of hydrogen, but you guys get the point for the process. You figure out the moles using ideal gas law. You take the mass of gas, divide it by the number of moles, and bam, you got the molar mass. Another thing that you can do, and I'll leave this to the assigned reading and the TRO text, but there's also a relationship between density and molar mass for a gas. And so density of a gas, because gases aren't that dense, we express density very often in terms of grams per liter. Okay, so grams per liter will be our density. And again, look at your textbook for the derivation of this, but we can say that the density will be equal to the pressure of the gas times, and they have like this funny fancy looking M, which stands for molar mass, and R times T. So again, this R here, you want to watch that. If your density is in liters, okay, your pressure is atmospheres, and that's in Kelvin. The moles, molar mass has moles. You can use the 0.08206. If, however, you have a different volume, in your density, like cubic centimeters or cubic meters or whatever, you're going to have to adjust R to have the correct unit of volume. But this equation right here allows you to relate the density of the gas, so this is the ratio of mass to volume, to the molar mass, which is the ratio of grams per moles. And again, look at your textbook. This comes directly from the ideal gas law, but it's a little square, dotted square around it, because it really is useful, and it's a useful way to get that molar mass experimentally. All right, so moving on to Dalton's law of partial pressure. This is one of the easier, I think, more obvious things, and that is that if you have a mixture of gases, okay, the total pressure of the mixture would be the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3, and so on and so forth. So by these partial pressures, backwards here, the partial pressure is just kind of the contribution of, you know, the pressure of each gas to the total pressure, and all this says is that they add up, and that seems pretty obvious. Now what I want to show you guys is a consequence of this. So if we express pressure in terms of the ideal gas law, so P is equal to nRT over V, okay, then what we get is that, you know, nRT over V, and we can do this for each one. Okay, so N2 RT over V plus N3 RT over V, so on and so forth. The volumes are the same for the gases because the gases fill up their volume. R is obviously the same. Okay, T is obviously the same. Okay, and so what we have here is that the total moles of gas is equal to the sum of the moles of all the gases. So again, that's a consequence of Dalton's law of partial pressure, and it makes it makes sense. You know, the N1, N2, and N3s. Okay, so what this means though is we can essentially, you know, we can set these things to each other. So what we can say is that, wow, this is really, what we can say is that the partial pressure of gas A will be equal to something called the mole fraction, okay, of gas A times the total pressure. So this mole fraction, this is mole fraction. And what we can say about mole fraction is that it's the moles of gas A, it's the number of moles of gas A divided by the total number of moles of everything. So essentially what this indicates is that the partial pressure of a gas is directly related to the number of moles of that gas. Okay, and it doesn't matter, you know, what type of gas you have, it just depends on the number of moles. Okay, so molar mass doesn't appear anywhere in here, identifying the gas never appears anywhere in here. So this is an important relationship. Okay, it's an important conceptual relationship that the moles of gas correlates directly with the partial pressure of the gas. And so if a gas has a higher partial pressure, you know, it's going to have a higher number of moles of gas as well. So I want you guys to look at this problem right here. So N2H4 decomposes at fixed temperature in a closed container to form those two gases. If the reaction goes to completion, what will the final pressure be compared to the initial pressure? So I'm going to pause the video, and I'm going to have you guys think about this and answer this question. A, B, C, D, or E, which one do you think is right? All right, so looking at this, what I want to do is I want to look at how many moles of gas did I have initially, and then how many moles of gas do I have at the end. So I'm going to make 2 moles of hydrogen gas, 1 mole of nitrogen gas. And so looking at this, if I have 1 mole of N2H4, I'm going to get 2 moles of this and 1 mole of that. And again, the identity of the gases, they don't matter. So essentially I can say, okay, I start off with 1 mole of gas, I end up with 3 moles of gas. Okay, so 1 mole, and then 3 moles. And this is what I was saying, that the pressure of the gas or mixture of gases correlates with the number of moles, not the identity. And so what I can say is that if initially the pressure is due to 1 mole of gas, if I now have 3 moles of gas, my pressure will be 3 times as great. And so C is the correct answer. Okay, and that is why. So those are the kind of the 2 new things. Make sure you guys read that textbook and take your notes, because there's more stuff in there that I'm going to want you guys to know. And if you have any questions, please ask me in class.